Hello, everyone. I want to welcome you to Greenville Technical College's International Education Week speaking event, hosted by the GTC Arts and Sciences Speaker Series. I am Associate Professor Jamie Roughton, and I would like to take a moment to introduce our distinguished speaker for this event. Today, we have the pleasure of hearing from Tim Armstrong, who is a senior meteorologist at the National Weather Service in Wilmington, North Carolina. In addition to providing forecast and severe weather warnings across 14 counties in coastal North and South Carolina, Tim also leads the office's climate data program. Originally from Western North Carolina, Tim graduated from UNC-Asheville with a degree in atmospheric sciences and has worked in Wilmington for 20 years. Tim has a true passion for meteorology, and I'm sure he's going to provide us with some fantastic insights on weather, climate change, and the impacts of both. If you have questions throughout the presentation, please feel free to message me directly in the chat box, and we will do our best to get those answered at the end of the session. Thank you for sharing your time and knowledge with us today, Tim. And with that, I'm going to go ahead and hand it over to you.
All right. Thank you very much for that introduction there, Professor Roughton. I'm coming to you live from Wilmington, North Carolina, the Atlantic Ocean, just a few miles off to my left today. And today's topic is going to be climate change, focused on the Cape Fear region here in southeastern North Carolina. But climate change, of course, is not a local phenomenon, it's global. So almost everything I'm going to speak about today will have direct applicability to you in upstate South Carolina or really anywhere else on Earth. So I'll go ahead and get the presentation started up here. Okay, and if that worked out, everyone should see a screen that says climate change in the Cape Fear region. So a little overview of what we're going to be speaking about today, the outline for today's talk, and this could be summarized also as sort of like where we were, where we are, and where we're going. We're going to start off talking about the difference between weather and climate. Are they the same? Are they different? What's the difference between those two very closely related terms? We'll look at a history of climate change over the Earth's history and the causes of that change. We'll look at more recent climate change, local observations as weather instruments were developed in the 17 and 1800s. We've been able to measure things like temperature with more and more precision. We'll look at the causes of recent climate change. And then the last part of the talk is going to be looking into the future. The climate is changing. It's going to continue to change in the future. How strong, how large are those changes going to be? And what are the impacts on society going to be from those changes? So starting at the top here, weather versus climate. So what is weather? Well, there's a nice little quote here, sometimes attributed to Mark Twain, although it's doubtful he really said this. But the quote is, weather is what you expect. I'm sorry, let me start over there. Climate is what you expect. Weather is what you get. And it sounds really short and pithy, something like Mark Twain might have said, but we're not really sure where that came from. But it's a really good way to summarize these two terms. Weather is the current state of the atmosphere, and current is really the key term there. It's what's going on right at this moment here. You can measure that temperature. You can use your eyes or satellite pictures to look at how many clouds are in the sky. You can use instruments to measure wind, rain, and so forth. But the key point here is that weather is something that's occurring in the short term. It's what's going on now. If you look at this continuum going from hours to days to months to years and decades and centuries of weather events here, on the left side of this here, individual thunderstorms, individual sea breezes, a hurricane, a cold front, these are all things that take place in a relatively short period of time. We would call those weather events. Now, if we change to the next slide here, climate is the observed weather averaged over a long period of time. So we're looking at now not the short-term aspects here, but we're going out months and years and even decades. We're looking at factors like El Nino and La Nina. You hear about that a lot with our wintertime forecast. You're looking at seasonal and annual changes in the climate over time. And of course, you go way out from decades into centuries, and we're talking about climate change. How does the climate change over centuries there? Again, the time aspect is the key difference here between weather and climate. It's how long a period are we looking at here? So that's sort of the idea I want to get across there. Weather is short-term, climate is long-term. Now, here at the National Weather Service, we're part of the big government organization called NOAA, the National Oceanic Atmospheric Administration, and we use a 30-year averaging period to compute our normals. So when we talk about what the average temperature is for a date or the average amount of rain or snow in a year, we're looking at a 30-year average. That was chosen because, number one, you want to get enough data points in there to derive a reasonable average of what's going on. But at the same time, you want to keep it short enough so that as the climate does change, you're able to change the measuring stick of what is to be expected right now to keep track with changes over time. And the little graphic I've got on the screen there for you is Wilmington's rainfall. We started taking rainfall measurements here in the year 1874, and you can see it changes a lot from year to year. Some years in the past, we saw just a couple of years that were over 60 or 80 inches. This year right here, 2018, was the year that Hurricane Florence came through. We had over 100 inches of rain in Wilmington. So a lot of year-to-year variability, but when I average that out over time, you can see a slow increase over time where we're finally up very close to 60 inches of rain on average a year now in Wilmington. So a lot of interesting ways we can keep track of data over history and look at what that tells us about what's normal and how those changes are occurring. Now, I mentioned that the Earth's climate has changed a lot in the past. If you were to roll back the clock about 21,000 years ago, and you went to go visit, let's say, the city of Boston, wanted to check a Red Sox game 21,000 years ago, you'd have a lot of trouble finding the city because it was buried under over 1 kilometer of ice. Over 3/4 of a mile thick, the great ice sheet that covered a large portion of North America, Northern Europe, and of course the North Pole of the Earth during that time period. That was its maximum extent about 21,000 years ago. Ice covered in some places over 2 miles thick across modern day Canada. And of course, this was natural climate change that had occurred all on its own here. This was the peak of the last ice age. Ice did not extend as far south as the Carolinas, but the climate that we had during this time period was significantly colder due to the fact you've got all that ice to our north. Ice being bright white reflects sunlight, and so it causes a feedback loop in the Earth's climate where so much sunlight that would hit the ground and be converted to heat is instead reflected back out to space. So the climate becomes cooler and cooler and cooler. But all on its own, the ice sheets did begin to melt. Now, if we look at a reconstructed temperature map of what the climate around the world looked like at the peak of that last ice age 21,000 years ago, the temperature anomaly where the ice was on the order of 20 degrees Celsius colder than it is today. That's about 36 degrees Fahrenheit, so significantly colder. Well, here in the Carolinas, we weren't covered by ice, but we were close enough that our average temperatures were about 10 or 11 degrees colder than they are today. So you're looking at a climate very similar to southeastern Canada, but it occurred right here in the Carolinas. So I'm sure that the plants and the animals that would have lived here were probably quite different at the time. Now, of course, this ice age did end, and you can see 21,000 years ago, that's about right here, the last glacial maximum. And as that ice melted off over a period of 10,000 years, global temperatures rose until they were very close to similar to what we're seeing today. That period began about 10,000 years ago. We call this the Holocene Era, sort of like the modern era of Earth's climate with the ecosystems and the plants and animals that we see today. And for about 10,000 years, we've had a very stable climate. Temperatures really not moving a whole lot. They cooled off a little bit here in the last 2,000 years, but then you'll see this spike here at the end. And that's what you hear a lot about in the news about the recent climate change. So one question you may be asking yourself is, well, I know there weren't civilizations, there weren't thermometers, there weren't really there wasn't a way to measure the weather. How do we know that these temperatures actually occurred like you're showing here? And the reason is when we go to areas that have large, stable ice sheets on Earth today, that could be areas like Greenland or like the center of the Antarctic continent. There's large ice cores that go down tens of thousands of feet. And if you drill down through that ice, you have records in there of the snow that actually fell and was compressed into ice. And you can actually see the annual variations in there. Now, for those who can remember their high school or maybe early college chemistry classes, we know that water is made of H2O. In other words, 2 hydrogens, 1 oxygen. Oxygen is the 8th element on the periodic table. So that means it has in its nucleus, we have 8 protons and 8 neutrons. But luckily for us who are climate scientists, about 1 out of every 4,000 oxygen atoms is actually a little bit different. It has extra neutrons. It makes it a little bit heavier. We call that oxygen 18 as opposed to oxygen 16. The heavier oxygen in certain water molecules makes it evaporate at a slower rate. It literally is heavier and less likely to evaporate. So when the Earth's climate is colder, more of that heavier oxygen in the water stays in the oceans. It doesn't evaporate out. So by measuring, when we go back to these ice cores, by measuring the amount of oxygen 18 versus oxygen 16 that's embedded in the ice, we can get an idea how readily was water evaporating out of the oceans, turning into snow, falling over these ice caps, and turning into these ice cores we're examining. You have basically a record of the Earth's average temperature embedded in these ice cores. And so by looking at that from various parts of the world, mainly Antarctica and Greenland, we can piece together a fairly long period of Earth's average temperature. And of course, you can't go back infinitely far into the past because there are periods back beyond where ice cores are available. But for the last couple 100,000 years or so, this is a valid technique to reconstruct what global average temperatures were. And that's how this graph came to you right here. Now, why did that ice age change? I mentioned about we had a feedback effect going on. You had all that white reflective ice reflecting sunlight back out into space, keeping the climate cold. What changed that to make that that ice no longer function as the break on Earth's climate, keeping us in an ice age? Well, the reason is the Earth's orbit around the sun may be unchanging, but the Earth's tilt, in other words, how tilted are the north and south poles from being vertical straight up and down over time. And that does change. There's a 41,000 year cycle. We call it the Milankovitch cycle, named after the physicist who first discovered this cycle. Over a 41,000 year period, the Earth's axial tilt actually changes from about 24.5 degrees at one extreme down to 22 degrees at the other extreme. That's only a 2.5 degree difference. How much difference could that really make? Turns out that's just enough to actually cause the changes we've observed in climate with the beginning and ending of ice ages over at least the past few million years. The logic goes like this. When the Earth is tilted more directly toward the sun, so 24.5 degrees, for example, there, the poles, the North and South Pole, receive a lot more sunlight during their summer seasons. That sunlight is actually able to get in around the edges of the ice and begin to melt it off. So it basically makes it less and less likely that large ice sheets can survive the relatively hot summers. Now, on the bottom of the screen, when the Earth's axial tilt is less tilted, so 22 degrees, for example, in that case there, the summer heat is less intense at the poles. There's literally less solar heating occurring there because the sun is lower in the sky. In those cases, it makes it more and more likely that snow and ice will survive the polar summers. And so you end up with growing and growing ice sheets. So over this 41,000 year cycle, you have periods of relatively intense heating at the poles, drives the ice away, or at the bottom there, you have periods of relatively weak heating during the polar summers, which makes it more likely for snow and ice to survive. Now, this does not mean simplistically that you would have an ice age every 41,000 years. There are other factors at work also in there, other tilts in Earth's orbit that occur over longer and longer time frames. But this is the primary driver for at least what caused the last ice age to end, is this Milankovitch cycle here, blasting just enough solar radiation in at the poles there to help to melt off that ice and bring us into the relatively ice-free period that we're in today. So back to this graphic again. We talked about what ended this ice age here 21,000 years ago. It melted off over 10,000 years. We've had a fairly stable and warm climate here the last 10,000 years, but then you've got this purple vertical spike here at the end. So let's focus in on that and see what's going on. So now instead of looking at 20,000+ years of data, we are looking at literally just like the last 150 years right here. This is global temperature change, 1880 through the year 2021. And you can see quite an increase here, especially in say the past 30 or 40 years, where global temperatures have increased quite dramatically. Now, this data has very small error bars on it because we have literally tens of thousands of thermometers installed at climate stations, at airports around the world now. We have weather satellites with finely tuned what are called radiometers that actually measure the temperature of the Earth, the oceans, the sky, the clouds, all these different scientific instruments now where we get very, very precise temperature readings of the planet that we live on here. In terms of the warmest temperatures we've ever seen, well, unfortunately, the last 7 years, 2015 through 2021, are the 7 warmest years that we've ever measured as a species here. That's these years I'm highlighting here at the very end. The year 2020 is tied with 2016, those two dots right there for the warmest air temperatures on record. I did check, we've got preliminary data that goes up through about September of this year, and we are currently running in that top 7 again. So it's going to be another very, very warm year. It does not appear we'll break the record this year, although next year, assuming that La Nina transitions to El Nino next year in the Pacific Ocean, the added heat from that oceanic circulation may help push us up to an all-time record next year. We'll have to see how that goes there. But essentially, this is the instrumented record now. where we've had thermometers installed at a multitude of stations around the planet where we can measure precisely the changes that are going on. So the greenhouse effect, you've heard about this before. This is partially what's going on to cause the recent increase in temperature rises here. Let's start off. What is the greenhouse effect? Essentially, if you've been in a greenhouse, like an actual glass greenhouse on a cold winter day, you'll know that just the sunlight being trapped by those panes of glass can cause it to be tropically warm even when it's freezing cold outside. That's essentially partially what our atmosphere does. The sun's heat comes down, strikes the Earth's surface, heats the air, heats the ground up, and so forth. A portion of that heat radiates back out into space, but a portion is trapped here at the surface of the planet by the atmosphere. And there are several key gases in the atmosphere that cause this effect. Water vapor is one, carbon dioxide and methane are others, and there are other smaller constituent gases that do the same effect there. But essentially, we need some greenhouse effect. If we did not have gases in our atmosphere that trap heat, number one, life would probably not exist here. But number two, models show us that if you remove the impacts of carbon dioxide, water vapor, and methane, the Earth's average temperature drops down to around 0 degrees Fahrenheit, currently 59 degrees Fahrenheit. So almost 60 degrees of warming caused by the greenhouse effect. Now, you can look at elsewhere in our solar system, and you can see what happens when the greenhouse effect goes crazy. On the planet Venus, that's the next planet closer to the sun from us, their average temperature on the surface is hot enough to melt lead, over 800 degrees Fahrenheit. They have a runaway greenhouse effect there. The atmosphere is mainly carbon dioxide and traps virtually all the heat coming in from the sun, which causes just a tremendous greenhouse effect there. Mars, the next planet farther out from the sun, has a very, very thin atmosphere. And even though there is carbon dioxide there, just not enough atmosphere to hold on to heat. So the average temperature of that planet is well below 0, making it unlikely life would exist there either. So we're sort of in this happy medium here with the atmosphere we have, where we are in terms of our position in the solar system, and the amount of greenhouse gases in our atmosphere that we have right now. Unfortunately, the amount of greenhouse gas in the atmosphere is not static. It has been rising. And this is a graph that goes back a little over 1,000 years, looking at the concentration of carbon dioxide, methane, and nitrous oxide. That's 3 of the greenhouse gases we can track pretty accurately. And you'll see that starting in around the year 1850, the concentration of these 3 gases in the atmosphere began to increase markedly. And what's going on here? That's about the dawn of the Industrial Revolution. That's when humanity first discovered, hey, we can burn coal, we can burn oil, and later on natural gas. We discovered that and power these amazing machines that make life really, really good for us. And it has been a success story of just really untold proportions. The modern life today, the amount of energy we have access to has been wonderful. But one of the unfortunate side effects of that is that we are changing atmospheric chemistry in a really, really fast way, really unlike anything else that we see on our climate record. Carbon dioxide, which previously before industrialization made up less than 300 parts per million of the atmosphere, is now over 400. And checked actually just a few days ago, we are currently at 418 parts per million, rising at about 2 or 3 parts per million every year. And that's due to the burning of fossil fuels, coal, oil, and natural gas. Those gases build up in the atmosphere. Methane, which is really, just think natural gas when you hear methane there, the same thing. The concentrations are setting new all-time records in the industrial era. Nitrous oxide, which is a gas formed when fertilizers are applied to fields and the bacteria break down some of those fertilizers and produce nitrous oxide gas. That's also building up in the atmosphere. Now, prior to, say, about 1920, 1930 or so, there weren't really instruments that people had built yet to measure the concentration of these gases in the atmosphere. But you'll notice that my graph goes all the way back to the year 1000. So where did this data come from? We're actually going to go back to the ice cores for this again. When snow falls in Antarctica or on the Greenland ice sheet, for example, air is actually trapped in and around the snowflakes. And as the snow falls year after year after year, and you get layers of this that press down harder and harder, you actually trap bubbles of air in the ice sheet itself. And by measuring with sensitive machinery what the constituent molecules were in there, you can actually see samples of air trapped from hundreds and hundreds of even thousands of years ago. That's how we're able to draw these graphs here. And when you see words on here like this sample is taken from the Law Dome or the WDC05A sample, that's actually just telling where it was taken from, what the core sample was. Some of these have sort of a lore almost in the scientific journals because they provided so much data for us over the years. But that's how we're able to tease out from the record left to us in nature and these ice cores what the air was actually like, hundreds, even thousands of years ago. So we are very, very lucky here in Wilmington. We have one of the oldest instrumented climate records of a continuous nature anywhere in the southeastern United States. Here in Wilmington, we began keeping rainfall records in the year 1870. And in 1874, we started keeping daily temperature records. So we have one of the longest unbroken strings of data for any station in the Southeast. We have the original climate books actually here in the office. Luckily, we don't have to go back and look at the old decaying paper there very often. We can keep those in a relatively pristine shape. About 30 years ago, those were digitized, actually put into a scanner, a flatbed scanner on a computer. And all this data was put into a database format. So now we can very easily look that up without having to go through these very, very old pages. But the handwriting on these old records is really, really spectacular. And we really owe a real big debt of gratitude to the folks who were able to spend their long, long nights recording these temperature and rainfall records for us to go back for so many years into history. If we look at Wilmington's data back to before the year 1900, we see that temperatures are rising here as well. Way back in the 1800s, our average annual temperature varied from, say, 63 to 64 degrees. We're now over 65 degrees here in Wilmington and continuing to rise. We have had a couple of years here recently where the average annual air temperature exceeded 66. So we are, of course, setting new records there. I mentioned earlier about rainfall. We are seeing rainfall records also being eclipsed here, where the climate certainly appears to be going toward a warmer and a wetter state here in Wilmington. And so that's just a little micro view of the climate change that is occurring across not just the Carolinas, not just the Southeast, but also around the rest of the world. So a neat way to look at how the climate has changed here in Wilmington. And again, this is not true just for Wilmington. We could put Greenville in here. We could put Columbia. We could put Atlanta in here. You're going to see pretty much the same factors take place. There's a lot of data on this graph. So let me try to explain how to look at this here. Let's look first at just this blue curve right here. And this is what's called a bell curve. For those who have some statistical background, you probably are familiar with the bell curve distribution of data. Let's imagine a very, very large Connect 4 board. Really fun game for my kids, I know that. Imagine in this Connect 4 board, on the left side, we've got the left column labeled as, say, 70 to 75, the next column 75 to 80, the next column 80 to 85, and so on like that. And I think there's 7 columns maybe in a Connect 4 board. And then every time that we have a daytime temperature between 70 and 75, we would drop one of the little Connect 4 checkers down in that little column there. And as you do this over the months and over the years, and even in this case over centuries, you would see a bell curve build up in the data here. And this is just for summer temperatures, but in Wilmington, the blue curve here is for the years 1891 through 1920. So over that 30-year period, the most common summer high temperature in Wilmington was about 86 degrees. You can see that occasionally you'd have highs only around 80. You'd occasionally have highs over 90. But for the most part, we were seeing highs in the mid 80s in Wilmington during the summer months. Now, run the clock up to the more present time, 2011 through 2020. The entire curve now, this is the red curve now, has been shifted over to the right. Now the most common average high temperature in the wintertime for Wilmington is 89 degrees. So we've literally picked up this blue curve from 100 years ago. We've shoved the entire thing over to the right, and we've warmed the climate, the summertime climate here in Wilmington, by about 3 degrees. So now really warm readings are more common, really cool readings are less common. Now, you may be thinking, and you're probably correct in this actually, I can't tell the difference between 86 and 89. I dress the same way. You probably understand that your air conditioning does run a little bit harder at 89 than 86. But for the most part, 3 degrees of difference is not going to change the way we live our lives. And you're absolutely correct. If that's the only difference, that things were about 3 degrees warmer, we wouldn't make any difference there. But here's where the problems start. Way back 100 years ago in Wilmington, we had a 95-degree day about 1% of the time in the summer. So that you're getting pretty far out on the bell curve there now. Now, in the year 2000, well, between the year 2011 and 2020, that's now 4% of the time. So we've seen a 400% increase. It's now 4 times more likely that you're going to have a 95-degree day in the summertime in Wilmington than what we saw 100 years ago. And 95 degrees, yeah, that's hot. That's getting to the point you don't really want to be outside very much. but still, that's, we can live in 95 degrees. Now, how about the 100-degree temperatures? This is getting up to where you have real societal impact starting now. This is where people really don't want to go outside. You've got to worry about school sports practices. You've got to worry about folks who are working outside as part of their jobs. 100 years ago, we hit 100 degrees in the wintertime, or I'm sorry, in the summertime in Wilmington, only about 1/10 of the time. That's now fully 1% of the time. And a summer day in Wilmington, we're at 100 degrees. That's literally 10 times more likely than it was 100 years ago. Now, you notice our graph stops right here. The highest temperature we've ever had in Wilmington, ever in history, 104 degrees. That was set back in a heat wave in the 1950s. We haven't had it yet, but what happens when we start to exceed that? What happens when Wilmington hits 105, 106, 107 degrees? That's never happened here before. What happens to our infrastructure when heat of that magnitude occurs that we did not plan for? If you remember the big northwestern heat wave that struck British Columbia, Canada, Washington, and Oregon in the United States back in late June, early July this year, there were places out there like Portland, Oregon. It's a coastal city that their normal summer temperatures are in the 70s and low 80s. They hit 116 degrees. They were not ready for that. Their power lines were literally dragging the ground and shorting out. Their roads were bowing up because as the heat works its way into the pavement, into the concrete or the asphalt, it expands. And their engineers never imagined they would have to allow for so much expansion for that kind of heat. So they literally had roads and bridges that were becoming impassable because the pavement was no longer level. We planned for 104. It's happened here before. Our infrastructure is set for that, but not 106 and 107. I checked just before this talk, and the highest temperature ever experienced at the Greenville Spartanburg Airport is 107. What happens if you hit 109 or 110? Can the power systems keep up with the immense electrical load to run the air conditioning? What happens to your roads and your water distribution systems and so forth? This is the real problem with climate change. It's not that we're 3 degrees warmer and that your daytime high, instead of being in the mid 80s, now the upper 80s. It's out here on the end of the curve, the improbable, well, that's not the right word, but the unlikely events now become more and more likely. And I guess things that were improbable in the past become more and more probable at time. That's where climate change is going to be the big, big problem for us in the future, I'm afraid. So there is actually a group even larger than the group I work for. I'm with the National Weather Service. There's a group called the Intergovernmental Panel on Climate Change, and they are the United Nations body that helps to organize and publicize the science related to climate change. I'm not directly involved with the IPCC. I did attend one of their regional talks a couple of years ago and help provide some input for what we're seeing here in the coastal Carolinas. But they come out with reports every several years. And their last report did mention that they believe the human influence in climate is clear, that we are having an impact on the climate. The greenhouse gases that we're generating are acting as a blanket to help trap heat that would have earlier in history radiated out to space. That's now warming the climate. And as we disrupt the climate more and more, we do risk severe and irreversible impacts to the world's climate. So here's some of the things that have come out of reports that are submitted to the IPCC. We're looking at temperature changes here across the Southeast. So this includes not just Wilmington, but also upstate South Carolina and the Greenville area. By the year 2070, we are expecting most of the southeastern U.S. to warm by an additional 3.5 to 4 degrees Fahrenheit. For Wilmington, that means our average temperature rises from 65 to about 69 degrees. In summertime is when we're expecting, unfortunately, the worst of these effects. That's when, due to the added moisture content of the atmosphere, you can trap heat more effectively in the summertime. So in the summer, we're looking at 4.5 degrees Fahrenheit increases above their current range. That's pretty bad news, since the summer heat is unfortunately what we're really focusing on for having fairly large societal impacts. We're also expecting changes in precipitation. And I'll just mention that for Wilmington, if you look at raising our average temperature by 3.5 to 4 degrees and raising our rainfall like we're seeing, that Wilmington's climate becomes a lot like coastal Louisiana is today. So if you like Baton Rouge, Louisiana, come to Wilmington in about 30 years. It's going to feel exactly the same. In terms of another societal impact here, energy use for air conditioning is probably going to increase by 30 to 40% across not just southeastern North Carolina, but really anywhere across the Southeast. The number of hot summer nights, those really, really sticky hot nights where the temperatures are in the 70s or 80s all night long, will increase by from essentially in Wilmington anyway, from about 25 nights a year now to 75 nights a year by the year 2070. So big societal impacts coming, both in terms of what the direct temperatures do to people outside, but also to what our electrical infrastructure is going to be forced to handle to run air conditioning in the future. I mentioned earlier about precipitation there. In a gross sense, the rainfall is expected to increase across the Southeast. That's mainly because warm air can actually hold more moisture in it. For every 1 degree Celsius you warm the atmosphere, you've increased the air's holding capability of water by about 7%. So just in an overall standpoint there, precipitation should increase at the same time that your temperatures are increasing. What is less clear, though, is how that's going to be distributed throughout the year. There are some models that show the interior portions of the Southeast, so unfortunately maybe upstate South Carolina back into the Tennessee Valley, becoming drier during the summer, which is pretty unfortunate, but maybe wetter the other times of the year. So there's still some developing research on that, but unfortunately things are going to change in that direction as well. One thing that does appear likely, and we are already seeing this, unfortunately, is that when it does rain, it's going to pour. That added capability for the atmosphere to hold on to water means that when it does rain, the rainfall rates are higher, so your risk of flooding is higher. So even if your annual average rainfall doesn't increase a lot, the number of, say, days with 2 or 3 or 5 inches of rain will probably increase fairly significantly above what we're seeing now. A lot of that here in the Southeast has been due to hurricanes. Of course, we've seen quite a number of those the last 10 years, bringing immense flooding. Most recently, Hurricane Ian down in Florida dropped, I think I saw totals of 26 inches in a few places between Tampa and Miami. Tremendous impacts there as well, unfortunately. Did mention hurricanes. I guess I skipped ahead a little bit here, but South Carolina and North Carolina, no stranger to flooding due to hurricanes and hurricane-like phenomena over the past 10 years. Hurricane Florence, of course, the big one here, at least for southeastern North Carolina. Back in 2018, we had 23 inches of rain here in Wilmington. It broke our previous rainfall record, not just for a single storm, but Florence's rain helped us to have over 100 inches of rain here in Wilmington, which blew the top off the old previous record. I will mention an interesting little tidbit about Florence there. Just a few years prior to Florence, I attended a meeting of the South Carolina Climate Office down in Columbia. We had a sort of a roundtable discussion to say, well, what is the highest possible rainfall from a tropical system here in the Carolinas? We knew that we were never likely to see the 40-inch totals like they saw in Texas with some storms in the past, but Hurricane Floyd back in 1999 had dumped over 20. So we sort of brainstormed and said, well, 25, 30 inches of rain is not out of the question. With Florence, we had a couple of spots, actually 2 stations that recorded close to 40 inches of rain, one up near New Bern, another one near Elizabethtown here in southeastern North Carolina. So Florence was just an unbelievable storm. You can, of course, never say that Florence was caused by climate change, but you can fairly safely say that the immense rainfall that Florence brought to the area was enhanced by climate change. And of course, other storms, Matthew brought tremendous flooding to eastern South Carolina. And there was even a storm back in 2015 called Joaquin that, although it stayed off the coast, never directly impacted the United States with wind. The rain, the moisture from that system was pulled inland across South Carolina and led to all-time record river flooding along the rivers between Columbia and the coast. So we certainly have seen a number of very heavy rainstorms impact the area. One way that you can actually play a hand in helping us to analyze how the climate is changing, there's a program called COCORAS, and you can actually go to the website here, cocoras.org. It stands for Community Collaborative Rain, Hail, and Snow Network. Essentially, you put a rain gauge in your backyard, you check it, and you type your data in on a website every morning. That goes to the Weather Service offices. It goes to water managers for cities. Local emergency managers can see this. Your data is also archived up at the National Climate Data Center in Asheville, becomes part of the permanent record of climate for the United States, and helps us to analyze how climate is changing over time. So a lot of good reasons there why you might want to consider joining this COCORAS program. And I'll mention that for Hurricane Florence, a lot of these totals here did not come from airports or from Weather Service observers. They were volunteer folks working with the COCORAS program. So we really appreciate the volunteer data that's being provided to us through this program and others. Now, one thing you won't have to deal with in upstate South Carolina, but we do deal with here on the coast, is coastal flooding. One of the things going on, and you probably heard about this, is as the Earth's climate warms, the ice sheets are melting, and that water is then flowing into the ocean and making the ocean levels rise. There's unfortunately a second part of that you may not hear as much about. That is, as the Earth's ocean temperature rises, the water expands in volume. It actually takes up more space for the same amount of water. So that's two factors, not just the fact the ice is melting, but the ocean itself is getting warmer, will actually cause the ocean levels to expand higher. Both of those are occurring, and here in Wilmington, we are a coastal city. The Cape Fear River at downtown Wilmington is tidal, connected directly to the ocean, so we have tides twice a day there. But we are noticing at high tides that more and more often here, especially since the year 2000, we are exceeding flood stage. We're getting water in parking lots. We're getting water on Water Street in downtown. We actually have had, with some of our more recent hurricanes, we've had flooding damage in some of the shops and businesses in downtown Wilmington that never used to happen. So it's not just a local phenomenon, but all around the planet, we are seeing rising ocean levels continuing to cause coastal flooding problems. Simulations of what's going to happen in the future unfortunately show us that as we get out toward the year 2050 and beyond, that ocean levels will be high enough to cause coastal flooding virtually every day of the year. So unless we raise our cities, or in some places they're putting up seawalls to try to stop the advance of the ocean, that you're going to see coastal flooding become a larger and larger problem going forward, not just in Wilmington, but at all coastal locations around the planet. So just to summarize, what are we seeing for anticipated impacts from climate change? Well, of course, warmer temperatures, that's the easy one there. Increasing the number of hot days, and that's going to have an increase on human, animal, and plant heat stress. I didn't mention agriculture specifically there, but obviously extremely hot temperatures when coupled with drought, you can kill a crop of cotton, corn, soybeans, anything that is being grown here in the Carolinas can suffer immensely due to heat at the wrong time of the year there. We're going to see an increase in energy usage for air conditioning. Hotter temperatures can evaporate water faster, so the possibility of drought will increase as well. If there is a positive in this, it's that we could see a decrease in the energy usage for winter heating. Now here in Wilmington tonight, we're going to have our first freeze of the season, looks like. We're forecasting 31 here in town tonight. So kind of an odd time to be talking about this, but energy bills for heating, it does look like in the future are going to be less and less going forward, just because our temperatures are going to be so much warmer. We are seeing larger rainfall totals that will lead to an increase in flooding severity. And of course, that rainfall may not be evenly distributed throughout the year, but a lot of the modeling on that isn't quite as certain as with some of the temperature impacts just yet. I mentioned sea level rise. Coastal property is going to be impacted as the sea levels rise higher and higher. With Hurricane Ian, of course, the storm after it crossed Florida came into South Carolina. We actually had some pretty significant coastal flooding between Charleston and Myrtle Beach. Even though Ian was a weakening Category 1 storm, relatively small fish on the big scale of things there, we still had one of our highest surges on record in the Murrells Inlet and Pawleys Island area, with pretty significant property damage. Again, I can't say that Hurricane Ian was caused by climate change. That's not a scientifically valid thing to say, but I can definitely say that the coastal flooding was accentuated by climate change, and that future storms that of Ian's intensity are going to cause more and more severe coastal flooding as sea levels continue to rise. And then the last thing that I did not mention really in there, ocean acidification. The primary gas that we're adding to the atmosphere that causes climate change here is carbon dioxide. When carbon dioxide dissolves into seawater, it forms an acid called carbonic acid. Now, the ocean is naturally an alkaline environment. That's why things like your oysters and anything that makes a seashell can actually take dissolved calcium ions out of the water, turn it into a shell that protects the creature. As the oceans become more and more acidic, as more carbon dioxide dissolves into the seawater, that process becomes harder and harder to do. The animals have to expend more and more energy, basically keeping their shells from dissolving in what is now a more and more acidic ocean going forward. It's unlikely, I think, that ocean acidification will play much of a role maybe in our lifetimes, but hundreds of years out in the future, I definitely see that causing some real issues, assuming that carbon dioxide continues to accumulate in the atmosphere as it's done for the past 150 years or so. Now, there are some really good resources on climate change I wanted to mention here. The North Carolina State Climate Office has basic climate science on their website. It's mainly from a North Carolina perspective, but I got to tell you that everything they say is directly applicable to South Carolina's climate as well, so you're welcome to look at that. Climate.gov is the official NOAA source for climate information. You can find everything in terms of the data that we produce on there, summaries that go back hundreds of years, and also outlooks for the future there. Globalchange.gov is the United States complementary website to the IPCC, where we put all the outlooks and reports on there that focus on impacts to the United States. You can look at the IPCC website. Has more of a global thing, global perspective going on there. I don't know that you'll find it quite as useful, although it is the official source for a lot of this information. There's also, if you really want to get local though, state by state, this statesummaries.ncics.org, that's run from North Carolina actually, and it will give you a state-by-state breakdown of what's going on with observed climate change up to this point in history and what's expected in the future. So some really good websites there that you might want to take a look at if you're interested in this. I've also got my contact information there at the bottom. If you can't find what you're looking for, I will do what I can to leverage the resources we have here and help find information for you to help answer your questions. So really appreciate you attending the talk today, and I will be happy to answer any questions that you might have.
All right, so if you have questions, thank you, Tim. We have really enjoyed this. This is a lot of very interesting and important information, and I can definitely say that I have learned a lot during this sharing. So if anyone has any questions, if you would like to send them to me in the chat, I will pose those to any. I don't have any yet, so just give people a second maybe.
Yeah, no problem. Yeah. And if you think of something later, my email address, timothy.armstrong@noaa.gov. I'd be happy to answer any questions you might have later on. While you're thinking of questions, I'll mention real quickly, the National Weather Service, we are the federal government organization that's in charge of forecasting weather, not just for 7 days out, but also we have a climate prediction service that goes out to a month in the future, trying to forecast month by month temperature changes. You probably know us most from our severe weather warnings, tornado warnings, severe thunderstorm warnings, flash flood warnings. That's us. We're a 24-hour operation around the clock, weekends, holidays. We're there watching the radar, making sure that you're aware of any weather hazards that might affect you and your family, your property, your business, and so forth. That's our primary goal, is the protection of life and property from weather and climate hazards. So we're certainly here to serve you 24 hours a day. Yeah, I focus here in Wilmington and the coastal Carolinas. There's an office at the Greenville Spartanburg Airport that services the upstate of South Carolina, also portions of western North Carolina. So we have agencies, over 100 offices around the country.
So I have some questions coming in.
Yes.
From George Abraham, we have, so essentially wet places are going to get wetter and dry places are going to get drier. So that's what he's asking.
Well, from a global perspective, or even just a regional perspective for the southeastern U.S., we see the climate actually getting wetter. And that's a consequence mainly the fact that warmer air can hold additional water. And so when it rains harder than it did before. You see more water accumulate in your rain gauge. Unfortunately, the flip side of that perhaps is that hotter temperatures mean that you're going to evaporate water at a faster rate than before. So if you get into a 2 or 3 week dry span in the summertime, which does happen, you're going to dry things out a lot faster than you did before. So unfortunately, it looks like that the extremes are going to become accentuated during climate change, that when it rains really heavy and your chance for flooding is higher than it was before. But when it doesn't rain during those periods, you'll dry things out faster due to the hotter temperatures. So I guess what you said there is it can be considered to be correct. From just a rain gauge perspective, though, we're all going to see more rain, it looks like, as time goes forward.
Okay. Hold on a second. So I have another question, and it is there anything that you would suggest that we as individuals can do to help with the climate change issues?
Yeah, I wish I could answer that. One of the things I've been told is that we need that the National Weather Service, because we're part of the federal government, needs to maintain an objective sort of hands-off part to activism. And while I may personally have, I personally drive an electric car, have solar panels in my house, doing some of those things like that, I can't from a government chair tell you to do these things. There are certainly organizations out there that are better handled to promote, green living that might have a lower carbon impact on the planet than I can. But I would certainly say just, Google some ways to reduce my carbon impact, carbon footprint, for example, and you'll find some really good resources. But from where I'm sitting, unfortunately, I can't tell you that today.
I understand. Um, so is there so this is no question, but great presentation. So they just wanted to tell you that.
I appreciate that. Thank you.
Yeah. And I don't have any other questions. I'll give it maybe a minute or two. I don't want to take up too much of your time. And so your follow up on the wetter and drier places, he laughs. He says, "So invest in HVAC companies, I think."
Perhaps so. Yes. Yes.
Yes. So that's but I don't see any other questions, but I do again want to say how much we appreciate your time and just what a wonderful presentation this has been. Very eye-opening with some fantastic information. And so I want to say thank you all for coming, and I hope you all have a wonderful day.